Alright, this video is about why matter is solid and how that's tied to the Dirac belt trick. And I was discussing the noncommutative torus with Sebs Solomon, and she just did a great video. She mentioned the non-commutative research of Alon Khan's, and then she posted a torus video about the donut as a torus, and then this video was recommended. I had already watched this video, and this is a real scientific video. I mean, it goes into all the abstract mathematics, and it's an hour-long video. So I suppose it's kind of boring, to watch. But as you get into it, they mention the torus right around here. You can see the torus, and anyway, as the video's about to end, they mention a neutron spin experiments that will then prove this we could even bring up the transcript, and we could search the transcript for neutron. Anyway, I can't really see the keyboard right now, but anyway, you could see over here, neutron. It's a long video. So the whole point with the neutron is there's no charge, and so you can actually see the spin, the 1/2 spin. And I commented how here it says right here, it goes, so it appears that nature is far more subtle and creative than we humans, because not only did she make these bizarre spin 1/2 objects, she made a whole universe out of them. But strangely, even nature isn't free to do whatever she wants. She is constrained, and constrained very severely, by the laws of mathematics. The non-contractible path in SO3 is simply there, no matter what. So while nature could devise a spin 1/2 particle, she could never devise a spin 1/3 particle, because the fundamental group of SO3 is Z mod 2 and not Z mod 3. And so while nature is creative, that creativity only exists within some very rigid and maybe even tautological bounds. And so he tries to bring that back to Plato, but it's really not Platonic at all. I mean, let's see here. So the SU2 is a double cover of SO3 and not a triple cover. And this is basically the double cover of SO3. That's the same thing as this, what Alon Khan's calls 2-3 infinity, as from music theory, the non-commutative secret of music theory. And I had made this connection in my first year of college when I took the quantum mechanics course. I knew that it was connected to music theory when I got taught. So here it says right here, Look up neutron interferometry for more details. Okay, so when you recombine the electrons, you'll find interference effects stemming from the minus sign. This exact thing has already been done with neutrons. So the 2 pi is the 360 degrees, but it has to be that turns it into it reverses the sign of the spin. So the reason they have to use neutrons is because there's no charge, so you're not affecting the spin can be shown directly. And so when he mentioned the neutron, this was what my physics professor did. He was the first one to recommend this neutron experiment in 1967. So then I found this article from 2010 from Australia. And so they're just saying a thought experiment with electrons that Ivanov and Zawisky and Jack Sarfati was just mentioning how he was with Zawisky around this time in the 60s. So they probably Jack Sarfati probably knows Herbert Bernstein also, because he was at San Diego, and I think Jack Sarfati was out in San Diego also with Fred Allen Wolf. So anyway, the fermions have 1/2 spin, and so when they're rotated by 360 degrees, they do not return to their original state like any macroscopic object, but they develop a minus sign in the wave function. So this, up until then, this was considered merely a mathematical artifact for this minus sign in explaining the Pauli exclusion principle that is responsible for the stability of ordinary matter. And so then they realized that neutrons would be needed to demonstrate the effect, so you don't get any Lorentz force from the electromagnetic field. And so then it says right here, as a matter of fact, a paper by Herbert Bernstein published almost simultaneously with the Aronoff-Susskind paper explicitly suggested neutron interferometry to demonstrate the effect. So then they explain this Pauli exclusion principle that causes the stability of matter. And they have these great Feynman diagrams. The reason for antiparticles. So this is also, it's not just the spin, but it's also antimatter. And that gets you into virtual photons. And anyway, the exchange of two particles corresponds to each being rotated 180 degrees right there. And then C would be 360 degrees of relative rotation. Or that's over here. So let's see, B and C corresponds to 360 degrees of relative rotation. So when you just look at this, it's hard to understand because it says that the minus sign, when rotated 360 degrees, then two identical particles in the same spin state cannot occupy the same position in space because they would interfere destructively if exchanged, hence the Pauli exclusion principle. Okay. So this also demonstrates the inherent non-locality of reality. This interference destructively is due to quantum entanglement. And so that's what Herbert J. Bernstein, my quantum physics professor, he also was the professor of Lee Smolin, who's a famous quantum physicist. So he recommended this in 1967. And so you have the two-slit interferometer, which is the entanglement of unpolarized neutrons. And this is the results can be the magnetic field is a doubly refracting medium, and so this is due to the entanglement. The opposite polarization experiences a decrease. And so here he's talking about that the torque would be an energy potential, which is another way of saying like reverse time energy, as the antimatter sort of. And so it's unambiguous. There's no unambiguous way of deciding. And so that's why you have to use a neutron, because there's no torque. The neutron's lack of charge allows us to disregard such deleterious side effects as Lorentz forces and the Bohm-Aharonov effect. So Professor Herbert J. Bernstein, he also held these Bohm dialogues, so he was into David Bohm also. And then he did a follow-up collaboration paper with Anton Zeilinger, who's like the most famous researcher of the Bell inequality experiment on quantum entanglement. And so what's really fascinating here is they say that in contrast, there are no momentum changes to be expected for a case of the purely time dependent, because it commutes with the momentum. And so they say that they're not using a wave vector, but instead the frequency of the wave function. So essentially they're not collapsing the wave function because of the entanglement, and then they're using the time. This is pretty much like a weak measurement experiment. So let's see if that's all I wrote, huh? Okay, so anyway, the whole point is it's much stranger. Like quantum physics, it's much stranger. The origin of reality is much stranger than we realize. It's not just a torus like a donut, but it's this. Like you really have to watch this Dirac video to get at the strangeness, because they go into the, like they show, let's see the, I don't want the sound on, but anyway, if you watch this video, it goes into the I mean, it's hard to conceptualize just how strange it is, you know. And of course, he gets in all the mathematics, and so it gets it's too abstract and it's too boring. But then he has these great computer animation graphics. This is, so right there, that's basically the Dirac belt, the Dirac dance, which is the 720-degree spin for each 0 point in space. And this goes back to Alain Kahn's noncommutative research. So yeah, he starts out with this kid doing or I think that's him. He's just a young, he's a young student, or a graduate or whatever. Anyway, so I recommend this Dirac's belt trick video, and then when they mention the neutron spin, then you'll have to watch this video is what explains. You can click on this article. They show the interferometer. See, it's all the way down in this thing. So, all these guys. Here we go. So that's the actual neutron splitter. Like these are equivalent of a half mirror for the entanglement by splitting the neutron, and they're using silicone. See if he explains it here. A beam splitter so let me see if I can. A diffracted beam emerging from it. The two diffracted beams continue on their way. I don't know. Splits it. Coherently split a beam of neutrons whose wavelengths are comparable in magnitude. Okay, so yeah, I mean, I don't understand all the details. Obviously, it's entanglement. How a neutron can be split, I'm not sure. Anyway, so the whole point is, like, just watch this Dirac dance, work your way through this, and he goes through the topology of the strangeness of the spin. And I'll just leave it at that.